Hello everyone, my name is Gehrlein. I'm based at Colorado State University, and today I'm going to tell you how we can track down the origin of neutrino mass. Let's get started on how we actually know that neutrinos are massive. This knowledge comes from the observation of neutrino oscillations, which also provides very strong evidence for physics beyond the standard model, and it introduced the need to generate now neutrino mass beyond the standard model. In the standard model, neutrinos are strictly massless, but now we know that neutrinos need to have a mass, so we have to account for the three neutrino masses. Then we also need to introduce the three neutrino mixing angles, as well as at least one more phase to our new model of nature. For more about neutrino oscillation physics, get over to the talk by Peter Denton, where he's giving an overview of what we already know about neutrino oscillations and how we test neutrino oscillations currently with current experiments and in the future. So generally, the idea behind neutrino oscillations is that we produce a neutrino of a flavor alpha with a certain energy E, and then the probability to detect a neutrino of flavor beta after it has traveled a distance L is given by this oscillation probability in a two-flavor approximation, which means we only assume that there are two different flavors of neutrinos. In nature, in reality, there are actually three. Nevertheless, this two-flavor approximation allows us to understand the basic principles behind it. The two important parameters in the neutrino oscillation probability, apart from the baseline L and the energy E, are the neutrino mixing angle theta, as well as this mass splitting delta Mij squared, which is defined as the difference between the neutrino mass eigenvalue Mi squared minus the neutrino mass J squared. This neutrino mass splitting dictates the frequency of this neutrino oscillation, which I'm showing here as a function of this ratio of baseline divided by neutrino energy, whereas this mixing angle theta gives us the amplitude of the oscillation. From our observations of neutrino oscillations, we know that at least two out of the three neutrinos have to be massive, whereas the lightest neutrino can still be massless. And we see from this oscillation probability that neutrino oscillation experiments are only sensitive to the difference between the neutrino mass, not to the absolute neutrino mass scale. Now that we know that we have to introduce neutrino masses to our new model of nature, the question arises, well, what kind of neutrino mass do we need to introduce? And unlike for the other standard model fermions, for neutrinos, two possibilities arise. The first possibility is that neutrinos are Dirac particles. Then the mass term looks like this. So we are coupling a left chiral neutrino to the right chiral neutrino via a Higgs doublet. And this mass term for neutrinos looks like all of the other mass terms for the standard model fermions. All of them obtain their mass via the coupling to the Higgs boson, and the coupling constant is this Yukawa coupling. However, for neutrinos, we also have another possibility, namely a Majorana mass term, which looks like this, where we are coupling the left chiral neutrinos to the left chiral charge conjugated neutrinos. Neutrinos are the only standard model particles which could have such a mass term, because neutrinos are the only standard model particles which do not have any standard model charge. This mass term namely breaks any U1 symmetries like electric charge. However, this term, however, is not gauge invariant. We are coupling two parts of a lepton doublet to each other. This is not gauge invariant. In any case, no matter if neutrinos are Dirac particles or Majorana particles, we have to introduce new particles to our model. In the case of Dirac neutrinos, we have to add this right chiral neutrino to our particle content. There are no right-handed neutrinos in the standard model. In the case of Majorana neutrinos, we have to add whichever particles lead to this Majorana mass term. So the observation of neutrino oscillation predicts new particles. But what is the neutrino mass scale? This allows us to learn about the required couplings in the new interactions, and this also helps us to identify promising experimental search strategies. So how do we measure the neutrino mass scale? From oscillations, we are not sensitive to the absolute neutrino mass scale, only to the difference between the different neutrino masses. There are two ways to measure the absolute neutrino mass scale. One is the kinematic measurement via the beta decay endpoint spectrum. So beta decays, you produce a neutrino, you produce a daughter nucleus, and you produce an electron. The maximum energy the electron can have is the maximum energy which gets released in this process minus the energy you have to invest into the rest mass of the neutrino. So by measuring the endpoint of the beta decay energy spectrum, so the highest energy electrons, we can see how much it deviates from the maximum released energy in this beta decay. There will be a very small difference of which is directly proportional to the mass we have to invest into the rest mass of the neutrino. It requires an extremely precise measurement of the electron energy. Currently, the Katrin experiment is pursuing this type of beta decay endpoint measurement, these are basically these data points here. As you can see, the search for neutrino mass started very early on, basically when the neutrino was first populated, and the bounds improved over time by several orders of magnitude. And nowadays, we still only have an upper limit, but we know that neutrinos are much, much lighter than the electron. In fact, the current upper limit on this observable in neutrinoless double beta decay, which is the mass of the electron neutrino, which is the sum over the different mass eigenstates, the three mass eigenstates of the neutrinos, Mi, multiplied by the PM&S matrix elements of the electron roll UEI squared. This gives us this observable M beta squared. The current constraint from the Katrin experiment is that M beta has to be smaller than 0.45 eV. The future reach of the Katrin experiment is down to 0.2 eV. After Katrin, new experiments like Echo Holmes, which uses electron capture, as well as the Project 8, can future improve the reach of this type of kinematic neutrino mass measurements. The other way to measure the absolute neutrino mass scale is via cosmology. And here I'm showing two different ways. On the left side, I show the impact of the sum of the neutrino masses on the CMB spectrum. And you see, depending on the sum of the neutrino masses, the CMB spectrum, particularly at low multipoles, changes. And also the matter power spectrum changes depending on the value of the sum of the neutrino masses. There are also constraints from current cosmological experiments. For example, Planck constrains the sum of the neutrino masses to be smaller than 0.1 EV, depending slightly on the data sets we are combining. And future cosmological observatories will measure the sum of the neutrino mass. They have a good enough sensitivity to tackle ultimately the sum of the neutrino mass instead of just giving an upper limit. And this is shown here. This is the observable, the sum of the neutrino masses on the y-axis as a function of the lightest neutrino mass, which again might still be 0. You see the current constraints in different horizontal lines. You see the future cosmological sensitivities. The purple line, this is what is expected in the inverted ordering. The blue line, this is the expectation in the normal ordering. Indeed, for both of these orderings, there's a minimum allowed value for the sum of the neutrino masses. You get that by assuming that the lightest neutrino is massless, but the other two neutrinos have to have a mass, because from neutrino oscillations, we know that we have two non-zero mass splittings. So these minimum allowed values are 0.06 eV in the normal ordering and 0.099 eV in the inverted ordering. So it's slightly larger in the inverted ordering than in the normal ordering. This can be contrasted with the most recent data from the DESI experiment, which measured baryonic acoustic oscillations combined with our constraints from Planck from the CMB. We get a current limit of 0.072 eV, which you can see is already slightly in tension with this minimum allowed mass in the inverted ordering, while normal ordering is still allowed. So a very exciting times for the cosmological measurement of the neutrino mass. Yes. So far we only have an upper limit on the neutrino mass. We also have a mild around 2 sigma preference for the neutrino mass ordering from oscillation experiments, which also depends on the combination of experiments. So there are two options for the neutrino mass ordering. Either the neutrino masses have a normal ordering or an inverted ordering. In the normal neutrino mass ordering, the lightest neutrino, which has a mass m1, has the most amount of electron neutrino. In the inverted ordering, the lightest neutrino, which has a mass m3, has the least amount of electron neutrino. Currently, we do not know which of these possibilities is realized. There is a small 2 sigma preference for the normal ordering, but we don't know yet, and future oscillation experiments are going to tell us which of these two mass orderings is true. So very exciting times here as well. So, however, combined like with the upper limit of the neutrino mass scale, a small preference for the normal neutrino mass ordering, we already know that neutrinos are much lighter than the other standard model fermions. There are several orders of magnitude lighter than the lightest standard model, next to lightest standard model fermion, which is the electron, and even more orders of magnitude lighter than the heaviest standard model fermion, the top quark. So is the lightness of neutrinos actually a clue about the underlying neutrino mass mechanism? Well, maybe. So for Dirac neutrinos, the Yukawa coupling has to be smaller than 10 to the minus 13. That is an extremely, extremely small number. And a much, much smaller number than the Yukawa coupling of the electron and the other standard model fermions. At colliders, because we can produce a lot of Higgses, we can actually probe the Higgs decay into fermions and extract the coupling, the Yukawa couplings. This has been done at CMS, but also at Atlas, and here you see the constraints we currently have. We have observed the Higgs coupling to top quarks, to W and Z bosons, bottom quarks, tau, and the muon recently. However, remember they have much larger couplings to the Higgs than the neutrinos could possibly have. So the direct probe of the Higgs decay into neutrino and antineutrino is just not possible. The decay rate is much too small. But is there any reason for the smallness of neutrino mass? Maybe. Remember the Majorana mass term for neutrinos is not, it breaks the standard model gauge symmetries. However, it can arise from higher dimensional operators. This means if we consider the standard model as an effective field theory with operators up to mass dimension 4, we can extend the standard model with its higher dimensional operators, dimension 5, dimension 6 operators, and so on. And all of these higher dimensional operators are suppressed by a high energy scale, typically called lambda. If Majorana neutrino masses arise from this higher dimensional operator, it is suppressed by this high energy scale. And indeed, it turns out that the Majorana neutrino mass operators occur at odd dimensions in the standard model EFT. That's dimension 5, dimension 7, dimension 9, 11, and so on. And the operators look like this. So you have to couple two lepton doublets, which contain the neutrinos, to two Higgs doublets, and then you can add higher and higher powers of Higgs doublets, so H dagger H. The resulting neutrino mass after electroweak symmetry breaking then depends on the coefficient of this operator, typically called the Wilson coefficient, the Higgs VEV, V, divided V squared divided by this high energy scale lambda, and then depending on the dimension of the operator, higher and higher powers of V divided by lambda. So if lambda is now much higher, larger than V, then you have the suppression of the electroweak scale coming from these higher dimensional operators. And if the suppression is really, really severe, then of course the resulting neutrino mass is really, really small. So that's the kind of the idea behind suppressing the neutrino mass with higher dimensional operators. So explicitly the dimension 5 operator, and in fact the only dimension 5 operator we can build with standard model fields only, is shown here. So two lepton doublets coupling to two Higgs doublets suppressed by one order of this high energy scale lambda, and there is some coefficient, Wilson coefficient, which is dimensionless. Now, since this dimension 5 operator is the only operator we can build with standard model fields only, and it has the least amount of suppression coming from this high energy scale, we expect that the first signs of new physics come from exactly this lowest dimensional SMAFT operator, which is exactly this dimension 5 operator, which means the first sign of new physics we expect is leading to a Majorana neutrino mass. Dimension 7 operators, again, two lepton doublets, two Higgs doublets, and another pair of Higgs doublets, or more Higgs doublets, basically, at higher dimension. But you see also the suppression by this high energy scale is now to the third power or to the fifth power. So these operators are more and more suppressed if this high energy scale is much, much above the weak scale. Okay, so this leads us to two different possibilities for the neutrino mass mechanism, either a Dirac neutrino or a Majorana neutrino. So do we have any theoretical bias? Maybe. So again, a Dirac mass term is present for all of the other standard model fermions. Indeed, some of them, since we have observed the Higgs decay into the heavy fermions already, we have already verified that this is the way the fermions mainly get their mass. From string theories, from the swampland conjecture, we expect that neutrinos have 4 degrees of freedom, which is a characteristic of Dirac fermions. And you can also take the standpoint that, well, we don't have a theory of flavor yet, which means we don't anyway know why the fermion masses are stretched across several orders of magnitude. Why worry that actually neutrino masses are even smaller than all of the other fermions? We don't even understand why the fermion masses are distributed in the way they are anyway. For Majorana neutrinos, well, neutrinos are different than the other standard model fermions. They do not have any electric charge. So maybe their mass mechanism is also just different because neutrinos are so different. Again, the only dimension 5 SMAFT operator we can write down leads to a Majorana neutrino mass term. So this is kind of what we expect as a first sign of new physics. Also, the dimension 5 operator, the suppression of this electroweak scale via this high energy scale lambda can explain the smallness of neutrino mass without the need to introduce a very small Yukawa coupling. So overall, we might have our theoretical bias, but ultimately, experiments have to find the answer if we have Dirac neutrinos or Majorana neutrinos in nature. So how do we do that? And that Andre de Gouveia is giving a whole dedicated talk about this in this workshop. So hop over to his talk if you're curious about how we actually answer the question Dirac versus Majorana neutrinos. Here I'm just giving a rough overview. So basically, how do we distinguish Dirac from Majorana neutrinos is to make use of the fact that the Majorana mass term violates any U1 symmetry associated to neutrinos. There is no standard model U1 symmetry associated to neutrinos, which is not already broken, but we can associate lepton number to neutrinos, and a Majorana mass term breaks this lepton number, whereas a Dirac mass term conserves lepton number. So we just have to look for lepton number violating processes. If we see them, then neutrinos have a Majorana mass term. If we don't see them, then they are Dirac particles and lepton number is overall conserved. The problem is that the effect of the lepton number violation is coming from the term which violates lepton number, which is the neutrino mass. So all cross sections, all decay rates which are lepton number violating are directly proportional to the neutrino mass. Indeed, the amplitude for any lepton number violating process depends on the ratio of the neutrino mass divided by the energy of the process. And neutrino masses are just so tiny that this ratio is just really small. So how do we test that lepton number violation? Well, the most promising way is called neutrino-less double beta decay. And this is a process where inside of a nucleus, atomic nucleus, two neutrons or protons simultaneously decay via beta decays. Double beta decay was first proposed by Maria Goeppert-Mayer in 1935. She also got a Nobel Prize in 1963. And this is basically the process. So you have simultaneous beta decay of two neutrons. So you emit two electrons and two anti-electron neutrinos. This happens in the standard model. This has been observed in several isotopes, germanium, xenon, tellurium, selenium. This is allowed in the standard model. The decay rate is really small. It's a very long lifetime for these elements. However, now, if neutrinos are Majorana particles, if lepton number is violated, then the neutrinos inside of the nucleus find each other, annihilate, because neutrinos are their own antiparticle if lepton number is violated. So you are not emitting the two neutrinos, you're only emitting the two electrons and the daughter nucleus. And this process can again only happen if lepton number is violated. And there are searches for this process, experimental searches. So far, we have not seen neutrino-less double beta decay. We have seen double beta decay with the emission of two neutrinos. However, there is also the Schechter-Walle theorem, which tells us that any operator which violates lepton number by 2 units and contributes to neutrino-less double beta decay will generate a Majorana neutrino mass contribution. So no matter what exactly is the underlying process, as long as you are violating lepton number by 2 units, you will generate a Majorana neutrino mass. However, from the non-observation of neutrino-less double beta decay, we actually get an upper limit of how large this contribution from this dimension, from this lepton number violating operators can be. And it turns out that the neutrino mass induced by any operators which violate lepton number by 2 units and contributes to neutrino-less double beta decay is of the order of 10 to the minus 28 eV. That's again an extremely tiny number. In particular, if you compare this induced mass to the lower limit we have on the second lightest neutrino. Remember, the lightest neutrino can still be massless, but we know that the other two neutrinos have to have a mass because from oscillation experiments we have measured two mass splittings which are non-zero. It turns out that the second lightest neutrino has to have a mass of at least 8 times 10 to the minus 3 eV. Many 25 orders of magnitude larger than this induced neutrino mass. which means neutrinos can have a large Dirac mass term and might still have a large Dirac mass term. Okay, so so Dirac versus Majorana neutrinos, but also if neutrinos are Majorana particles, there are different possibilities, different opportunities to generate the neutrino mass. Again, coming back to the fact that the Majorana neutrino mass operator can come from a dimension 5, dimension 7, or dimension 9 operator, or higher dimensions. Also within these operators, you have two possibilities. So generally for dimension 5 operator, the neutrino mass depends on the coefficient, the Wilson coefficient of the operator, the Higgs Webb squared divided by this high energy scale. You can either explain the smallness of the neutrino mass via a hierarchy argument. This means that the higher the new physics scale, so lambda is very, very large, and the smallness of the neutrino mass comes from a suppression of the electroweak scale by this very high energy scale lambda. Problem is, since we associate lambda with the mass of a new particle, we are not going to see this particle directly. So we have no direct probes of these new particles we introduce in our neutrino mass generation mechanism, and we introduce a new high energy scale, which makes the question of like all of the scales we have in the standard model worse. So that's the hierarchy problem. Nevertheless, you can pursue this way of explaining neutrino masses, in particular their smallness, in a type 1, type 2, type 3 seesaw scenario. The other idea to explain the smallness of neutrino mass is via a symmetry argument. Here, lambda does not have to be extremely large. It can be small, small meaning around like the electroweak scale or maybe slightly higher. And the smallness of the neutrino mass comes to a small Wilson coefficient C. Since lambda does not have to be extremely large, the new physics particles whose mass is around the scale of lambda, we can actually test them and produce them at colliders. This can be pursued in a type 2 seesaw, in an inverse seesaw, linear seesaw, and extended seesaw. The last three seesaw types are mechanisms or variants of a type 1 seesaw. Okay, so for Majorana neutrinos, you have three different, or you have multiple possibilities depending on the dimension of the operator, but within a certain dimension of the operator, you still can distinguish if you want to explain the lightness of neutrino mass via a hierarchy argument, where you only have phenomenology at a high scale, or via a symmetry argument, where you have a phenomenology at a lower energy. So you have a lot of possibilities to explain the neutrino mass. And there is another one, which is neither Dirac nor Majorana. So neutrinos could be pseudo-Dirac, which means there is a small lepton number breaking contribution to the neutrino mass. However, the dominant contribution to the neutrino mass is of Dirac nature. So the neutrino mass has some Majorana contribution, some Dirac mass contribution. The Majorana mass contribution is much, much smaller than the Dirac mass contribution, since the amplitude of any lepton number violating processes depends only on the Majorana neutrino mass term divided by the energy. That's extremely tiny, which means even though fundamentally neutrinos are Majorana fermions, because lepton number is broken if they have a Majorana mass term, they behave to a very good approximation as Dirac neutrinos in all experimental settings, because this contribution, this lepton number violating amplitude, is just so heavily suppressed. Okay, so we have a lot of possibilities. Now let's look at these possibilities of neutrino mass generation in more detail. So we can look for the new particles associated to the neutrino mass generation. For Majorana neutrinos, we have to identify UV complete models for the higher dimensional operators. I'm just focusing on the dimension 5 operator, which has three different realizations. They are called the type 1, type 2, type 3 seesaw. In the type 1 seesaw, you introduce a standard model singlet, typically called a right-handed neutrino. In the type 2 seesaw, you add an SU2L scalar triplet to the standard model, which couples to the Higgs and the lepton doublets. In the type 3 seesaw, you add an SU2L fermion triplet, which couples to the Higgs and this lepton doublet. So let's first look at the type 1 seesaw. Again, you add a new standard model singlet fermion to your model. The neutrino mass in this scenario depends on the coupling of the Higgs to the left to this new fermions and the lepton doublet. That's the Yukawa coupling squared times the Higgs wave squared, divided by the mass of these right-handed neutrinos. And now you start to see why this is called a seesaw mechanism. The larger this sterile neutrino mass, the smaller is the mass of the active neutrinos, the neutrinos we see. So it's like a seesaw. One goes up, one goes down. So how do we probe the existence of these right-handed neutrinos? Well, the interactions of the sterile neutrino or right-handed neutrino with the standard model are governed by the active sterile mixing angle. Theta, which depends on the ratio of Yukawa coupling Higgs wave divided by the mass of the right-handed neutrinos. And then the neutrino mass depends on this mixing angle times another factor of Yukawa coupling times Higgs wave. So the neutrinos we observe, if we have this active sterile mixing, a mixture of like the active neutrino, the ones which interact with the W and the Z boson, and the sterile neutrino, which is a total standard model singlet, so it does not directly interact with any of the standard model gauge bosons. And this admixture is governed by this active sterile mixing angle. Now, since the neutrinos, since only, a fraction of the neutrino we observe interacts with the standard model gauge bosons, that's the active neutrino fraction, we can compare neutrino interactions basically to see if some part of the neutrino is actually sterile. And this is done experimentally. Now, how to probe the presence of a sterile neutrino depends on its mass. So it also depends on which active neutrino the sterile neutrino is mixing with. So if the sterile neutrino mixes with the electron neutrino, the mu neutrino, or tau neutrino, and the x-axis is like the sterile neutrino mass. Light sterile neutrinos with a mass around the EV scale can be constrained with cosmological observables because they behave effectively like another neutrino. You can also constrain light steriles by looking at mu neutrino disappearance. They will act as a new frequency in neutrino oscillations. You can also look for light sterile neutrinos up to a mass around like the MeV scale typically by looking at beta decay endpoints, the same way Katrin is trying to measure the standard model neutrino mass. You can also constrain the presence of heavier neutrinos because the electron endpoint spectrum is moving further and further away from its maximum value. You can also test the presence of sterile neutrinos with a mass around the keV scale from supernova and X-ray observations. Heavier sterile neutrinos with a mass between the MeV and the GeV scale. You can look for them in meson decay experiments. Again, similar idea as with beta decay experiments. You look at the maximum energy of the produced charged lepton in meson decays like pion decays or kaon decays or D0 decays for the mixing of the sterile with the tau neutrino. Heavier sterile neutrinos above the GeV to the TeV scale, you can test at colliders. You just produce them directly and you observe their decays. At even heavier sterile neutrinos, you cannot observe them directly anymore. You have to resort to their indirect effects. And this goes under the name of non-unitarity of the PM&S matrix, because now you don't have only 3 neutrinos anymore. You have additional sterile states. So the 3 times 3 mixing matrix we can observe in neutrino oscillations is in reality an n times n mixing matrix, we are only seeing the 3 times 3 sublog, which then, of course, is non-unitary. The whole mixing matrix, the n times n mixing matrix, that is unitary. It has to be unitary. But the sublog, the one we observe in neutrino oscillations, is non-unitary. So by observing a lot of neutrino oscillations, as many channels as possible, we can constrain the unitarity of the neutrino mixing matrix. Okay, so these are now the constraints for the mixing between the active neutrino and the sterile neutrino on the y-axis as a function of the sterile neutrino mass on the x-axis. And here you see all of the different experiments. Again, they do fall into the groups I've just shown you. So some beta decay endpoint experiments, some meson decay experiments, and then at higher energies, the collider experiments. You also see this dashed diagonal line. This is the line we expect from a type 1 seesaw because there is a direct relation between the neutrino mass, for which we have an upper limit, this active sterile mixing angle shown on the y-axis, and then we know the Higgs wave, we just assume a large Yukawa coupling. However, note, so that is kind of the diagonal line is kind of our target. You see that actually none of these experiments really touch the target yet, because as you can see, the heavier the steriles, the smaller is this active sterile mixing angle, the less is the contribution of the sterile state to the neutrinos we actually observe. So it's making it harder and harder to actually really see or touch this predicted line. Nevertheless, these searches are really interesting because the sterile neutrinos do not need to be related to the neutrino mass generation mechanism. You can just add a standard model singlet fermion to the standard model. It does not need to follow this dashed line, basically this relation here. The active sterile mixing angle does not have to be related to the neutrino mass. The addition of a standard model singlet fermion to the standard model just generally goes under the name of a neutrino portal. Okay, moving on to the next. The type 2 seesaw, where we introduce a new scalar field, which is charged under SU2L and charged under hypercharge. This leads to neutral, singly, and doubly charged scalars. The neutrino mass depends on this Yukawa coupling, the coupling of the lepton doublet to this scalar triplet, and the coupling of the scalar triplet to the two Higgs fields, mu, divided again by the mass of the scalar triplet. Also here, the heavier the mass of the scalar triplet, the lighter is the neutrino mass. So again, a seesaw mechanism. So since you have new particles which are charged under the electroweak standard model gauge symmetry, you can look for this new particle with electroweak precision observables. You can look for it at colliders. You can look for it in charged lepton flavor violation. You can look for it in G-2 experiments. Again, we haven't seen anything yet, so a lot of exclusion bounds coming from this publication here. The white region is still allowed, and typically we can only test new particles at colliders up to like the TeV scale or so. Above, at heavier masses, we don't really have any good direct constraints, but yes. Type 3 seesaw, it's kind of similar to a type 1 seesaw. So now we introduce a fermion field, a triplet fermion field, which is again charged under SU2 and U1 hypercharge. However, the neutral fermions basically play the same role as this right-handed neutrinos in a type 1 seesaw, but now you additionally also have charged fermions and the neutral fermions. Since the whole field is charged under the electroweak symmetry, they now have interactions with the electroweak gauge bosons. Again, the neutrino mass depends on the Yukawa couplings, Higgs wave squared, divided by the mass of this new triplet scalar field. Again, a seesaw mechanism, the higher the mass of the new particles, the lighter the standard model neutrino mass. So now you also have mixing not only between the neutral fermions, the neutrino, and like the neutral component of this fermion triplet, but also between the charged fermions. And you can also probe these new particles via electroweak interactions. Yeah, so you can look for it at colliders, you can look for it at charged lepton flavor violation constraints. Again, the white region is allowed. All of the colored regions are different constraints from different experiments. Okay, so this was the hierarchy explanation behind the smallness of the neutrino mass in like the different seesaw mechanisms. We can also look at the symmetry protected neutrino mass models. Here again, the smallness of the neutrino mass comes from a small Wilson coefficient. The new particles do not have to be heavy. And as an example, we can look at the inverse seesaw mechanism, which is a variant of a type 1 seesaw mechanism. You see that is the diagram. It very much looks like a type 1 seesaw. You are introducing now two copies of right-handed neutrinos, N and N prime. They have different lepton numbers, but the diagram looks kind of similar to what we had in a type 1 seesaw, with a crucial difference that now there is a coupling between the two N primes, which is given by this mu parameter, which is dimension full. So the neutrino mass now depends on mu, Higgs wave times U cover coupling squared divided by, sorry, the mass, the mass term between n and n prime, which is mn squared. So if mu is of the order of keV, you get a neutrino mass of the range we expected with sterile neutrinos, which have a mass at the TeV scale such that we can test it at colliders. But why is mu at the keV scale? It is again several orders of magnitude below the 100 GeV, the electroweak scale. So now we introduce yet another scale to our problem. Can we motivate the presence of a keV scale? The answer is yes. In the dynamical inverse seesaw, so we identify this mu parameter now as the VEF of a scalar field. So we make it dynamical, so the scalar S breaks some gauged B minus L symmetry in this particular model. It obtains a VEF, and the VEF can be identified with this mu parameter if this breaking happens at a specific scale. The VEF basically plays the role of this mu parameter, and we can explain why it arises. We can do something similar in a type 2 seesaw mechanism. Also there, the neutrino mass depended on the coupling of the scalar triplet to the two Higgs doublets, which again was called mu. Also here we can identify mu as the VEF of some scalar field. The scalar field breaks some symmetry, so it's a dynamical parameter now, and we can explain its smallness in some model realization. Another idea to explain the smallness of neutrino mass is to look at radiative neutrino mass models. Here, the smallness of mu is due to a loop factor, and there are 1, 2, and 3 loop neutrino mass models available in the literature. They have different characteristics, different new particles which get introduced, for example, leptoquarks, or the C-Babu model where you introduce new charge scalars. They all have in common that the neutrino mass now arises not at tree level, but at loop level, which gives you a loop suppression factor. The higher the loops, the more suppression you have, the lighter you can make the new particles you're introducing, the easier it is to test them. Okay, so what will we learn by testing the neutrino mass mechanism? Well, we will first learn which particles do we need to add to the standard model. Is lepton number a conserved symmetry of the standard model or not? That's the question, Dirac versus Majorana. We are getting closer to explain the flavor puzzle. Why all of the fermion masses are distributed across so many orders of magnitude? This can motivate and streamline future work. Depending again on the question, Dirac versus Majorana, we can also explain the baryon asymmetry of the universe via a leptogenesis mechanism for Majorana neutrinos. We can do something similar for Dirac neutrinos called Dirac leptogenesis. We also learn if neutrinos have other characteristics. So Dirac versus Majorana neutrinos have different electromagnetic moments, which can motivate experimental searches. Okay, now let me summarize and conclude. So neutrino oscillations provide very strong evidence for the need of additional particles related to the neutrino mass generation mechanism. There are many possibilities. We have a maze of possibilities to generate neutrino mass. All of them have their own rich phenomenology. However, so far, we have not seen any new particles. If a new particle is discovered, we need to test if it actually can play a role in the neutrino mass generation mechanism, if it matches all of the other global particle physics data sets we have. So future improved experimental sensitivities and new testable models will hopefully bring us closer to finding a neutrino mass generation mechanism. Okay, thank you very much. And I'm looking forward to discussing with you in the discussion sessions. Thanks.